Welcome to our deep dive into trivial dependencies, a crucial concept in database normalization. To understand trivial dependencies, we must first introduce functional dependence. In database design, we use the arrow notation B determines A or B goes to A to show functional dependence. Column A depends on column B when each value of B determines at most one value of A. This is the core concept of functional dependence. Now let's define what makes a functional dependency trivial. A functional dependency is considered trivial when the columns of A are a subset of the columns of B. For example, consider a composite key. Fair class is always determined by the combination of flight code and fair class itself. This is always true, and thus, a trivial dependency. But why do we care about labeling these dependencies as trivial? It relates directly to meaningful database design. Since trivial dependencies are mathematically automatic, they don't provide valuable, non-obvious information about your database structure. That's why they must be excluded when we are defining normal forms. We only want to focus on meaningful design information. The exclusion of trivial dependencies is central to the definition of Boyce-Codd normal form, or BCNF. A table is in Boyce-Codd normal form if, for all non-trivial dependencies, the determinant, B, is a superkey or unique. By focusing only on non-trivial dependencies, BCNF ensures that we are properly eliminating redundancy based on genuine data relationships. Let's look at a quick example to contrast trivial and non-trivial dependencies in practice. Trivial dependencies like, quote, fair class depends on flight code and fair class are ignored. They don't need to be checked for BCNF compliance. However, any non-trivial dependency must be checked. We must verify that the determining column is unique to ensure a dependency is valid for BCNF. To wrap up, remember the key role of trivial dependencies in normalization. Excluding trivial dependencies is how Boyce-Codd normal form guarantees efficient, redundancy-free database design. This precision in analyzing non-trivial relationships is what makes BCNF a powerful tool for structural integrity.
So we have ISO, MKIB, Is it the country name? Is it the capital name? Is it the continent name? Let's see the country name. So let's look at the table. So you have the ISO, you have the country name, you have the capital name, the continent. Then the rows examples are like Macedonia, Europe, Indonesia, Asia. So the first question is asking, what columns depend on ISO? So ISO here is the unique identifier for each country. So therefore, the country name, the capital name, the continent name all depend on ISO. So the correct answer here would be the country name, the capital name, and the continent. Let's get to see the country name, the capital name, and the continent. What columns depend on the capital name? So each capital city is unique to a country in these areas. So from capital name, you can determine the country name. It is ISO code and its continent name. So the correct answer here will be the ISO, the country name, and the continent name. Let's just see. So all the boxes are checked. Let's check. We got it right. Yeah. So the country name, capital name, continent name, ISO, country name, continent name. ISO is the primary key of country. So all column depends on ISO. So each capital is one country. So ISO and country name depend on capital. So each capital is in one continent. So one continent name depends on the capital name. Okay, let's get to the next question. So the next question is that the table has columns A, B, C, D. And the country name is ABC, ABE. The primary key is ABE. Dependency is A to C. Addition dependency on the candidate keys. So what is the normal form table? If, for example, if a table is in its first and second but not third form, select second. Alright? So let's get to see in details just to understand what we've been asked so that we can come up with the right explanation. So what we are seeing here, is that we have columns. So the columns has A, B, C, D. The candidate key has A, B, D. The primary key A, B, D. The dependency A to C. So first, normal form 1NF. Yeah, all contributes are atomic, so no repeating groups or multi-valued attributes. So the table is 1NF. Okay. Second, normal form, that is 2NF, requires 1NF and no partial dependency. So no non-key attribute depends on part of a composite key. Okay. So here the key is ABD dependency. A to C means C depends only on part of the composite key A. So this violates the 2NF. Now let's look at the 3NF situation. So you require 2NF and no transistive dependency. So non-key dependency depending on other non-key attributes. So the table already falls in 2NF, it cannot be 3NF, right? So the Boyd's code normal form requires that it's stronger than 3NF and requires that every determinant B to be a candidate key. So since A is not a candidate key but determines C, so B, C, and F is violated. So when we are looking at 1NF, we have all attributes, no repeating groups or multi-valued attributes. When you're looking at 2NF, we have no non-key attributes and it does not depend on composite key. When you're looking at 3NF, we have non-key attributes depending on other non-key attributes. And we have Boy's code normal form. We have we must have a candidate key. So the correct answer here is the first normal form. And let's get to check our answer, and it's correct. So the table has one candidate key, which is also a primary key. So any table with a primary key is in the first normal form. So the table is not in second normal form since the non-key column C does not depend on the whole primary key. Let's go to the final question. So you have the table that has A, B, C, D. The candidates key are A and C, D. Then you have dependencies C to B in addition to dependencies on key candidate. And when you're reversing table all and create new Boy's code form, so they're asking what columns are revised table all, table new, and table new key. So here, in other words, what they are asking here is that, so we have the table all, which has column A, B, C, D. Candidate keys are A and C. Dependencies are C to B. So step 1, identify the violation. In B, C, and F, every determinant must be a candidate key. So here, C to B is a dependency, but C alone is not a candidate key. This violates B, C, and F. Step 2, decompose the table. We split the table into two relations to remove the violation. So we have table new to capture the dependency C to B. So column CB, primary key C. So since C determines B, then revise table all remaining attributes with proper keys. So column A, C, D, candidate A, C, and D. So this structure actually satisfies B, C, and D because all elements are candidate A. So the final answer here is for the revised table all. The answer will be A, C, D. For the table new, so for the revised table all, A, C, D, right? So for table new is CB. Table new will be C and B. And for the old, for the table new primary key will be C. So let's check. And we got it right. So we have finished this section.